Welcome to another deep dive. We're going to be looking at this chapter from a physics textbook you sent us,
Okay, great.
and looks like it focuses on ray optics and optical instruments.
Lots to unpack there.
Yeah, so get ready to learn how some of those really cool optical illusions work,
Right?
how things like fiber optics, make the internet possible,
Yeah.
even how telescopes let us see into galaxies that are millions of light years away.
It's going to be fun.
It is. All right, so light.
Yeah.
I mean, it's something that we experience constantly, but I don't think we stop to think about how it actually works that often.
It's true. It's how we see the world, obviously, but it behaves in ways that can seem almost magical.
Yeah. So starting with the basics here, we know that light travels extremely fast, but how fast are we talking?
So get ready for this. Light travels at a speed of roughly 299,792,458 meters per second in a vacuum.
Whoa.
Yeah, to put that in perspective, that means it could circle the Earth over 7 times in just 1 second.
Wow. Okay, that's mind-boggling. I can't even imagine something moving that quickly.
It's the fastest speed achievable in nature.
And we generally visualize light traveling in straight lines.
Yes,
And physicists call these rays, right?
exactly. You can picture a laser pointer. That beam that you see is essentially a concentrated stream of these light rays in action.
Makes sense. So we really see those rays when we talk about mirrors.
Right.
But this chapter goes beyond your average flat mirror. It goes into these curved mirrors.
Yeah, curved mirrors.
They sound complicated.
Well, so we have 2 types. Concave mirrors, which curve inward,
Okay.
and then convex mirrors, which curve outwards.
Right.
And they each have their own interesting effects on the light rays that hit them.
So they do more than just reflect an image like a regular mirror.
Exactly. Because of their shape, curved mirrors can actually focus or spread out these light rays,
Okay.
which means they create images that can be real or virtual, magnified or diminished,
Yeah.
and even flipped upside down.
It's like those funhouse mirrors, right?
Exactly, those funhouse mirrors that make you look super tall or really wide.
Yes.
Yeah.
And those distortions aren't just random, right? This chapter mentions something called the mirror equation and the magnification formula.
Yeah, and they sound complicated, but they can actually predict how an image will look
Really?
based on the curve of the mirror and how far away the object is from it. So yeah, imagine taking a selfie in a funhouse mirror. These equations could actually predict how distorted and weirdly proportioned you'll look.
Oh my gosh, that's so cool.
Yeah.
It's crazy to think that there's these formulas that can predict those things. This chapter also had this really cool example about a jogger
Okay. Yeah.
running towards a car's side view mirror,
Right.
which I'm guessing is a convex mirror.
It is, yeah.
And it said that because of that curve, the speed of the jogger's image in the mirror actually changes,
Yes.
even though they're running at a steady pace in real life.
It's a great example of how these curved surfaces can really distort our perception of motion.
Wait, so the jogger's reflection is speeding up in the mirror, even though they're running at a constant speed?
Yeah.
That's so trippy. So clearly mirrors are more than meets the eye, pun intended.
Definitely.
But this chapter also goes beyond reflections and talks about refraction.
Right, so refraction describes how light bends when it travels between different mediums, like from air to water.
Okay.
You can think of the classic broken pencil illusion that you see when you put a pencil in a glass of water.
Okay, so light bending is what makes the pencil look broken.
It is, yeah. It's because light actually travels at different speeds in air and water. So when those light rays go from one to the other, they change direction. And that bending, that's what makes the pencil appear broken.
Makes sense. And that also explains why a swimming pool seems shallower than it actually is, right?
Absolutely. Because the light coming from the bottom of the pool, it bends as it travels from the water into the air. Our eyes perceive the bottom as being closer than it really is. You can think of it like our brains are kind of misinterpreting where the light is coming from.
Wow, light is very sneaky.
It really does play tricks on our perception of reality.
This is so fascinating. Now, the textbook kept mentioning Snell's law when talking about refraction. What is Snell's law and how does it fit into all of this?
So Snell's law is a key principle in optics. Imagine shining a flashlight into a pool at night. The angle at which the light hits the water and the angle at which it travels underwater, that relationship is what Snell's law describes. It helps us predict how much a light ray will bend.
Oh.
So yeah, it's all about the angles.
I see. And this bending depends on what the textbook calls the refractive index, right?
Yes. Imagine light as a swimmer. When it enters a denser medium, like water, it slows down. just like a swimmer would encounter more resistance.
Okay,
This slowing down factor, that's what we call the refractive index.
gotcha. So water has a higher refractive index than air, which
Yeah.
is why the light bends more dramatically when it goes from air into water.
Exactly.
Okay, this is all making sense now. The next part of the chapter really blew my mind.
Okay,
Total internal reflection. It sounds like light gets trapped.
that's a great way to put it. Yeah. Under certain conditions, when light travels from a denser to a rarer medium, it can actually be completely reflected back into the denser medium, as if it hit a mirror. This happens when the angle of incidence, that's the angle at which the light hits the boundary, is greater than a specific value called the critical angle.
So it's like a point of no return for the light. It tries to escape, but it's forced to bounce back in.
Precisely.
Wow.
Yeah, and this phenomenon has some really incredible applications. Think about the prisms and binoculars. They use total internal reflection to bend light and create that compact design.
Oh, wow. I never realized all that complex physics was going on inside a simple pair of binoculars.
It's pretty cool. And it gets even more impressive. Total internal reflection is actually the backbone of fiber optic technology.
Really?
Yeah, this is how we transmit information as light pulses over vast distances.
Wait, so you're telling me that, like, the internet basically runs on light bouncing around inside these tiny glass fibers?
That's essentially it. These fibers are specifically designed so that the light signals stay trapped inside,
Wow.
bouncing off the walls because of total internal reflection.
Okay.
And this allows data to be transmitted incredibly fast with minimal loss of signal strength.
This deep dive is making me realize how much I take light for granted.
Yeah.
It's amazing to see how this one phenomenon can be responsible for, like, everything from rainbows to the internet.
It's pretty wild.
It is.
And we've only just scratched the surface. Next, we'll delve into the world of lenses, which are essential for understanding how our eyes, cameras, telescopes, and countless other optical instruments actually work.
All right, I am ready to dive into lenses and see what other secrets light has in store.
Let's do it. Okay, so we've covered how light travels at crazy speeds,
Right.
how mirrors can kind of trick us,
Mm-hmm.
and how that total internal reflection thing makes fiber optics possible.
It's wild.
It is wild. So now let's talk about lenses.
Okay.
These carefully crafted pieces of glass, or sometimes other transparent materials,
Yeah.
can really shape and control light in some remarkable ways.
Okay, I have to say, lenses have always been a bit mysterious to me. I mean, I know they're in my glasses,
Right.
my phone camera, like all sorts of things.
All over the place.
But I don't really get how they work.
Yeah.
It's almost like magic.
Well, yeah. It can feel like magic, but it's really about using those principles of physics that we've already talked about to manipulate light. And at the heart of it, lenses work by bending light or refraction. Remember how light changes direction when it travels between, mediums with different refractive indices?
Right, like the broken pencil in the glass of water.
Exactly.
So are lenses basically just playing with that bending to create different effects?
Yeah, exactly.
Yeah.
So by carefully shaping the lens, we can control how those light rays either convert or diverge as they pass through it.
Mm-hmm.
So a convex lens, which is thicker in the middle,
Mm-hmm.
causes those light rays to kind of converge or come together at a single point called the focal point.
Okay.
Think about a magnifying glass focusing sunlight into a tiny, intense spot.
Ah, so that's how a magnifying glass works.
That's how it works.
That makes so much sense. What about concave lenses, the ones that are thinner in the middle?
Right.
What do they do?
So concave lenses, they do the opposite. They cause light rays to diverge or spread out.
Okay.
You might not see them used as often as convex lenses, but they do have some important applications.
Like what?
So for example, they're used in some types of telescopes
Oh, okay.
and to correct certain vision problems like nearsightedness.
Interesting. Okay, so I'm starting to see how different lens shapes can have completely different effects on light.
Exactly.
The textbook also mentions something called the lens maker's formula.
Right, the lens maker's formula.
I have a feeling this is where things are going to get really complicated.
Well, it sounds intimidating, but it's actually a pretty intuitive formula. It basically tells you how strong a lens is at bending light based on the curvatures of its surfaces and the refractive index of the material it's made from.
Okay,
So in simpler terms, it helps determine how powerful a lens will be.
got it. So higher refractive index, more powerful lens?
Exactly. Materials with a higher refractive index, they bend light more dramatically.
Mm-hmm.
That means they could achieve a shorter focal length, resulting in a more powerful lens. Remember that analogy of light as a swimmer?
Yeah.
A higher refractive index would be like swimming through honey. It really slows you down.
Right. I also remember the textbook compared lenses to like a bunch of tiny prisms working together.
Yeah, that's a good analogy too.
That one really helped me visualize it.
Yeah. And just like with mirrors, we have a special formula for lenses.
Oh, no. Is there like a lens formula that's different from the lens maker's formula?
It's not as complicated as it sounds. The lens maker's formula, that tells you about the power of the lens itself.
Okay.
The lens formula is all about how images are formed by the lens.
Right.
So it describes the relationship between where the object is, where the image forms, and the focal length of the lens.
Okay. So the lens formula is about predicting how that image will look based on where the object is.
Yeah.
Okay. And all of this really just comes down to the way that the lens is bending the light, right?
Exactly. Just like we could trace those light rays with mirrors, we can do the same thing with lenses.
Okay.
And there are rules that help us predict exactly where the image will form, how big it'll be, and its orientation.
Wow.
All thanks to the way the lens bends the light.
So cool. Okay, so thinking about multiple lenses, the chapter mentioned how like modern smartphone cameras use a whole stack of lenses
Right.
rather than just one.
They do.
I've always wondered how that works.
Yeah. So that's a great example of how we can combine these lenses to achieve very specific optical effects. So in a smartphone camera, those multiple lenses work together like a sophisticated team. Each lens kind of playing a specific role.
Yeah.
They're all working together to focus the light,
Okay.
zoom in and out, even correct distortions,
Right.
all to capture a really clear and sharp image.
So it's like each lens is compensating for the limitations of the other one.
Exactly. They work together to create a final image that's much better than any single lens could achieve on its own. And those same principles of combining lenses, that's what allows us to build some of the most powerful scientific instruments out there,
Right.
like microscopes and telescopes.
Okay, so microscopes allow us to explore the tiny world of like cells and bacteria. And telescopes let us gaze at these like distant galaxies.
It's amazing.
And both of them rely on those same basic principles of optics that we've been talking about, right?
It really is remarkable how those same fundamental laws of physics govern, both the very small and the very large.
Right.
And in both cases, it really comes down to the way lenses manipulate light
Okay.
to reveal things that would otherwise be invisible to us.
All right, I'm ready to zoom in on those incredible instruments and see how they use lenses to expand our vision in such dramatic ways.
Sounds good.
So we've gone on this incredible journey through the world of optics.
We have.
Figuring out how light travels, those crazy mirrors, refraction, even lenses.
Lenses.
And now I feel like the grand finale.
Yes.
We're going to explore how all of those principles come together to make these incredible instruments.
Amazing.
Microscopes,
Yeah.
telescopes.
Get ready to zoom in and zoom out.
Exactly. I'm ready for some serious magnification.
It's mind-blowing how these tools have really expanded our vision,
Yeah.
letting us see things that were once, totally hidden from us.
Right.
From the intricate details of tiny cells to the vastness of distant galaxies.
It's amazing.
It's all thanks to the clever manipulation of light.
I remember using a microscope in school, being completely captivated by that microscopic world.
Oh, yeah.
Seeing those tiny cells for the first time felt like discovering a whole new universe.
I agree.
But I have to admit, I never really understood how it worked.
Right.
Beyond okay, it makes things look bigger.
Well, the basic principle behind a simple microscope is actually pretty straightforward.
Yeah, okay.
It's essentially a powerful magnifying glass,
Okay.
a convex lens with a really short focal length.
Okay, so a simple microscope is basically like a supercharged magnifying glass.
Pretty much, yeah.
Makes sense.
By placing the object very close to this lens within its focal length, you create a magnified image that's upright and virtual.
Gotcha. So I can see how that would work to magnify tiny objects.
Right. But to achieve even greater magnification, we use something called a compound microscope.
A compound.
And instead of just one lens, it uses two lenses working together.
Two lenses, all right.
An objective lens and an eyepiece lens.
Okay, like a tag team of magnification.
Exactly.
How does that work?
So the objective lens, which is the one closest to the object, it does the heavy lifting first. It creates a real, inverted, and magnified image of the object. This image then acts as the object for the eyepiece lens.
Okay.
The eyepiece lens then magnifies that first image even further, creating the final virtual image that we see.
It's like a magnification relay race.
Yeah.
Each lens passing the image to the next for even more magnification.
I like that analogy.
Mm.
And the total magnification you get with a compound microscope is simply the product of the magnifications of both lenses.
So to get super high magnification, you need both lenses to have a short focal length.
Exactly. And the distance between those two lenses, which is called the tube length, also plays a role in the overall magnification.
Okay.
But, magnification is only one part of the story. Microscopes are also carefully designed to illuminate the object properly.
Right.
And to minimize any distortions, so making sure we get a clear and accurate magnified image.
Right. So there's more to it than just making things look bigger.
It's true.
It's a whole science to creating that high-quality, magnified image.
Definitely.
Okay, so let's shift gears.
Right.
We're going from the microscopic to the cosmic.
Telescopes.
Telescopes.
Yeah.
So they work in a similar way, right? Using lenses to magnify distant objects.
You're right. The basic principle of using lenses to magnify is definitely shared by both.
Okay.
However, telescopes are designed specifically to magnify objects that are really far away, like stars and planets.
Yeah.
They have to gather and focus light that's traveled millions, sometimes billions of light years to reach us.
Wow, they must be incredibly powerful to do that, but how do they actually work?
Okay, so let's start with the classic type of telescope,
Right.
the refracting telescope.
Right.
It uses two convex lenses, just like a compound microscope,
Okay.
an objective lens, but this time with a long focal length, and an eyepiece lens with a shorter focal length.
Right.
So the objective lens gathers light from that distant object and forms a real inverted image at its focal point. Then the eyepiece lens takes over,
Okay.
magnifies that image to create the final virtual image that we see.
So it's like a compound microscope, but on a much larger scale.
You got it.
And with a different purpose. It's crazy that the same basic arrangement of lenses can be used to explore both the incredibly small and the incredibly distant.
I know, it's a testament to the power of these fundamental principles of optics.
Yeah.
And just like with microscopes, the magnification of a telescope is determined by the ratio of the focal lengths of those objective and eyepiece lenses. But with telescopes, there's another crucial factor: light-gathering power.
Right. The textbook mentioned that a telescope's light-gathering power depends on the size of that objective lens. Is that why telescopes need to be so big?
Precisely. A larger objective lens has a greater surface area, which means it can collect more light from those faint, distant objects. Think of it like collecting rainwater. A bigger bucket will catch more water than a smaller one.
Right.
So the more light a telescope can gather, the fainter the objects it can see and the more detail it can reveal.
That makes sense.
Yeah.
And speaking of big, the textbook mentioned some telescopes have mirrors that are 10 meters in diameter.
Oh yeah, those are reflecting telescopes.
Okay.
Instead of using a large objective lens to gather and focus the light, they use a large concave mirror. This actually allows for the construction of much larger telescopes, which helps us push the boundaries of what we can observe in the universe.
So it's like a workaround for having to build those massive, massive lenses.
Exactly.
This deep dive has really been an eye-opener. I never realized how much incredible science is packed into something as seemingly simple as light.
It's amazing.
From simple reflections to the super intricate workings of microscopes and telescopes, it's incredible how light shapes our understanding of the universe.
It really is.
Yeah.
And you know what? What we've explored today is just the tip of the iceberg. Oh yeah. The study of light encompasses so much more.
Wow.
From the wave nature of light to the revolutionary technologies being developed in fields like photonics and quantum optics. It's a field that's constantly evolving and pushing the boundaries of human knowledge.
Wow. It sounds like there's always more to discover in the world of optics.
Always more to discover.
Well, I think this deep dive has given our listeners a fantastic foundation
Absolutely.
to go out and explore this fascinating field even further. So, to our curious listener, take a moment to appreciate the wonder of light in your everyday life. From the colors of a sunset to the twinkling of stars, light is a constant source of beauty and discovery.
It really is.
Maybe this deep dive sparked a passion for optics. That will lead you to explore even more. Thanks for joining us on this illuminating journey.
Until next time, keep looking closer.